Hey everybody, it's Thursday, September 24th. As you can see here in the AIM, today we're going to be talking about one-dimensional motion and how we can use our knowledge of one-dimensional motion to solve what I refer to as complex constant velocity problems. Now, we ended yesterday on a bit of a cliffhanger by taking a look at one of these. And so we're going to go through that problem and talk about some of the general concepts and then get to one more nice complex constant velocity problem that I generally refer to as the chase problem. And then that will basically be it for constant velocity motion. We'll hopefully, depending on how long this video ends up being, set ourselves up perfectly to dig into accelerated motion to finish up the week on Friday. Just as a few general reminders, there was homework up in the stream. The homework solution sheet was attached to this post, so you should take a look at that. Of course, ask me any questions if you have them. We'll address those in the Zoom or by comments or emails. And there's another set of problems for you to get in some practice tonight, and the homework solution sheet will be posted tomorrow. So, yesterday, we left off at the very end of the video by taking a look at this problem, which is on page 19, number 27 of the one-dimensional motion packet. It says, you hike 2/3 of the way up to the top of the hill at a speed of 3.0 miles per hour, and then run the final third at a speed of 6.0 miles per hour. What was your average speed? Take a second to think about that. Now, if we were in class, I would probably ask you the question, what do you think the average speed is? Who has an idea of what the average speed is? And the most common answer we get, first at least, every year without fail, is 4.5 miles an hour. And I say, why? And they say, well, the first speed that's given is 3, and the second speed that's given is 6. And so the average of those two numbers is 4.5. Makes sense. It's wrong, but it makes sense. What's actually happening in this problem is a little more complicated than doing just a straight up average. And so let's get into it. The first thing we could say about this kind of problem, which I generally refer to as complex constant velocity problems, is that when solving an average velocity problem where the person spends unequal time intervals, that's the most important part here, unequal time intervals at multiple speeds, we cannot just take the ordinary average of the two speeds. When they spend unequal time intervals at multiple speeds, we cannot just take the ordinary average of the two speeds. In order to use the two speeds to determine the average speed, you must calculate a weighted average, which is weighted in terms of the time and not the distance. That's an important point because that's usually the next answer that's offered up. Well, people say, well, they spend 2/3 of the time at 3 miles an hour, and they spend 1/3 of the time at 6 miles an hour. And well, 2/3 of 3 is 2, and 1/3 of 6 is 2. So the answer is probably 4. Take those two numbers and you add them together. That's not it either, because when you do these problems to determine the average speed, you have to calculate this weighted average, weighted not in terms of the distance, but in terms of the time. And I'll show you what I mean by that in a minute. Another piece of advice here for answering this question would be if you're not actually given distances in the problem, but fractions of the total distance, as they do here, you can just make up the distances, and you should just make up distances that preserve the ratio of each distance to the total distance. And so in this problem, they say 2/3 of the distance and 1/3 of the distance. So just as long as you pick any set of distances where one of them is 2/3 of the total and the other is 1/3 of the total, then you're in business. Take a second to pause this video if you want to finish writing that down, because I'm going to move on to the next slide. Big note here. In order to find the average speed as the weighted average between two speeds, you must find the weighted average in terms of the speeds being weighted for the time spent at those speeds, not the distances traveled at those speeds. Now, you pretty much wrote that down on the last slide, but this part is crucially important, so I want to make sure to emphasize that. You have to find the weighted average in terms of the time and not the distances. And so here's a list of steps that I want you to follow when we're doing these questions. Step 1, make up distances that preserve the ratio. You're not always going to have to do this, but sometimes you will if they don't tell you the actual distances, but rather just tell you the fraction of the distances. This step, to some degree, is optional. It depends on the problem. Step 2 is to find the times for each part of the trip. And then step 3 here, the last step, is to use this weighted average equation. Now I want to dig into this equation a little more, and I'll do that on the next slide. So here we go. There's the equation. As you saw on the last slide, I'm still using the pen? Yeah. As you saw on the last slide, there was a bar over this V. Sometimes you will see that, sometimes you won't. You don't always have to write that. It's not that big of a deal. I am going to write that for these, just really, if nothing else, just to differentiate between the V1 and the V2, that this is the overall average speed. But as I'm sure you probably know from math, average quantities or mean quantities usually have a bar written over them. So there's the equation. V, and again, we could put the little bar over it, means average velocity. That's our average velocity measured in meters per second. V1 is the velocity traveled by the object on the first segment of the trip. In this case, that would be 3 or 6. It doesn't really matter which one you call first and which one you call second. I usually do them in order, but it doesn't really matter. V1 is the velocity on the first trip segment. V2 then, obviously, is the velocity on the second trip segment. Now, I showed this here for 2 velocities because, number 1, that problem I just showed you only had 2 velocities, and number 2, I don't remember a problem from the packet of questions I have for you where they show you any more than 2 velocities, but it's important to realize these like sort of ... this ellipses, that's what that's called, by the way, if you don't know that, is implied for this kind of thing. If they give you 4 trip segments, then the next term would be T3 over T total times V3, and then T4 over T total times V4. And then, of course, the T's corresponding to the first and second trip segment are labeled as T1 and T2, and then, rather obviously, I think, T with the subscript T there is the total time of the trip. And so going back to that list of instructions, you need to make up distances that preserve the ratio, find the time that would be spent at those distances, and then use this equation. Again, why we can get away with making up distances, because if the distances preserve the ratio, then these 2 times will preserve the ratio as well. Because notice, not what we need is not the actual time, but it's the fraction of the time that would be spent at that speed. And that fraction will be preserved for any distances you pick. All right, let's take a look at how to do this problem. It says you hike 2/3 of the way to the top of the hill at a speed of 3 miles an hour and run the final third at a speed of 6 miles an hour. What was your average speed? I like to show this problem a few different ways.
Okay, so in this problem it says you hike 2/3 of the way to the top of a hill at a speed of 3.0 miles per hour and run the final third at a speed of 6.0 miles an hour. What was your average speed? So I want to pick distances that make sense here. That's going to make the math nice and easy. I'm not going to have to think that hard. It'll be pretty simple, pretty easy. And like I said, it really doesn't matter. And so I'm just going to pick distances. I'm not going to think that hard. I'm going to pick 40 miles and I'm going to pick 20 miles. Notice the thing that's easy about the 2/3, 1/3 thing is that we all know that 2/3 is twice 1/3. So if we just pick one distance that's twice the other, 40 and 20, then we know it's going to work. And in this problem, they tell us they spend that 40 miles going 3 miles per hour and the 20 miles going 6 miles per hour. Okay. So the first thing that we need to do after we've made up distances is find times. And so we can say here, just to make our list, V1, the velocity on the first segment of the trip, is 3 miles per hour. D1, the distance, is 40 miles. V2, the speed on the second part of the trip, is 6 miles an hour, and I guess I should write 6.0 and 3.0 because that's what it says in the problem. And then D2 is 20 miles. And what we're looking for, ultimately, is the average velocity. And everything that you have to find in between, you don't have to write down that variable as an unknown. I do sometimes just to keep track of it, and so I'll do that here, just so we're all keeping track of it, because there's a lot of moving pieces of this problem, as you'll see. So the first thing that we need to do, like we said in our list of advice, was to find the times that would be spent at each part of the trip. And so I'm going to say that V1 is equal to D1 over T1. So that means T1 is going to be D1 over V1. And when I do that, I take my 40 miles divided by my 3 miles an hour, and 40 over 3 is 13 1/3. And so I'll write just something like that. We're not going to go nuts about sig figs. It's 13.33333 repeating hours. And so I'll take that and I'll put that in a box and I'll leave that off right here at the top. Now we'll do the same thing, but for trip 2. And we can show in exactly the same way that the time on trip 2 is going to be equal to V equals D over T. So that would be V2 equals D2 over T2. And so we get T2. The time for the second part of the trip is D2, the second distance, over V2, the second speed. And so we get 20 miles. Notice we're going to get a totally different time here because we have a smaller distance. 20 miles as our distance, 6 miles per hour as our speed, which is a bigger speed. And we get the second time is 3 1/3, right? Because 20 over 6 is 3 1/3. And then that's hours. Okay, cool. So those are the times. And we can also find the total time. if we'd like. And the total time, obviously, in a very straightforward way, is just the sum of the individual times. So we have T1 plus T2. And that means the total time is going to be 13 1/3 hours plus 3 1/3 hours. Right? And 13 3 is 16. And 1/3 plus 1/3 is 2/3. And so I'm going to write 16.66 repeating hours. So now looking back at the weighted average equation, we needed V1, we got it. V2, we got it. T1, we found it. T2, we found it. T total, we found it. And now we're in business. So all we have to do here now is plug into the weighted average equation. Because I don't want to forget these or make a silly mistake. I'm going to go back and just retroactively add these times to my list before I erase the rest of this here. So T1 is 13 1/3 hours. T2 is 3 1/3 hours. And the total time is 16 2/3 hours. All right. We're almost there. Last thing we got to do, just to round this one off, is to use our weighted average equation. Our weighted average equation says that the average speed is equal to the ratio of the times V1 plus the ratio of the second time and the total time times V2. And so putting all that together, we have 13.33 hours over 16.66 hours times 3 miles per hour plus, just separate all that, plus 3.33 hours over 16 2/3 hours. Now, as it turns out, if you put in your calculator just like 13.333333, like a bunch of threes, and you put 16.6666 and a bunch of sixes, and you divide those two numbers, what you actually get is an easy, clean number. It's 0.8. They spend 80% of the time at 3 miles an hour. Whereas 3 1/3, if you put in your calculator all the repeating decimals, divided by 16 2/3, is actually only 0.2. So they only spend 20% of the time at 6 miles an hour, which makes sense because they're going a smaller distance and they're covering that smaller distance at a larger speed. And when we do that math and we add them together, 0.8 times 3 plus 0.2 times 6 gives us an overall average speed of 3.6. Yes, it is true that 2/3 of the distance is spent at 3 miles an hour, but 80% of the time is spent at 3 miles an hour. And that's why the average speed is so much closer to 3 miles per hour compared to 6 miles an hour. Even though it's 2/3 of the distance, it's 80% of the time. And so that's why the average speed ends up being 3.6, so much closer to 3 than 6. But of course, the obvious question here is like, how do you know I'm not just wrong about this? Like, how can we really confirm that the answer is not just 4.5? Like, makes sense, or why it's not just 4 like we would get when you weight the distances. Well, at the end of the day, if you really want to be that annoying, it's a joke obviously, we can always go back and confirm the answer here using our good old-fashioned v equals d over t. Average speed is a ratio of distance to time. And so at the end of the day, we can always do this. Just as a quick check, 40 and 20 are two distances, gives us a total distance of 60 miles. Our time total is 16.666666 repeating hours. And when you do that math, 60 divided by 16.666666 repeating, of course, you get 3.6 miles an hour. The speeds need to be weighted in terms of the time and not the distance, because average speed is a ratio of distance to time. And so it is the fraction of the time that matters, not the fraction of the overall distance. That's the key detail. Of course, we could just take the total distance and divide it by the total time, but you don't want to get sort of sucked into making a silly mistake by accidentally weighting the averages in terms of the distance, or even simpler than that, than accidentally just taking the literal average of the two speeds. Because as I hope this example is put across now, that doesn't work.
And that's how you solve one of these complex average velocity problems. You just have to make sure you're being careful about which technique you choose. The last thing I want to mention before we go, though, because I know the first time I saw this, I was very skeptical about the whole you can choose any distance part. Like that just confused me. I didn't like that. I didn't buy it. And so I want to just show you, on my own notes, I decided to solve this 2 ways just for fun to show it. And so we can just say here, in this first example, I chose 40 and 20 as my distances, but what if you chose 4 and 2? The point here is you get the same answer. All right, I'll just zoom it out that much. You're going to have a different total time. You're going to have a different total distance. You're going to have a different T1 and T2. But again, none of that actually matters because it's all about the ratios. So here, this is just like a quick solution without all the work shown. If you found the first time, V equals D over T turns to T1 equals D over V, right? D1 over V1. And you get 4 miles divided by 3 miles an hour, and that would give you 4/3 of an hour. Simple. The second time on trip 2 would be T2 equals D2 over V2, and that would give you 2 miles over 6 miles an hour, and that would be 1/3 of an hour. The total time you get by adding these two things here, and it's 4/3 of an hour plus 1/3 of an hour, very obviously gives you 5/3 of an hour, and that's our total time. And when you plug this into just a good old-fashioned V equals D over T, 6 miles over 5/3 of an hour, it gives you 3.6 miles an hour. What do you know? But of course, if we plug it into the weighted average formula, it works too. Notice before I said the time spent at 3 miles an hour was 80% of the total, and the time spent at 6 miles an hour was 20% of the total, and those ratios work here too. 4/3 is 80% of 5/3, and 1/3 is 20% of 5/3, right? Because 1 is 20% of 5, yeah? Okay. And 4 is 80% of 5. And so when we do this weighted average, never show work like this, by the way. I don't even have the equation or the equal sign there, but if you take 0.8 times 3 miles an hour plus 0.2 times 6 miles an hour, of course, you get 3.6. So it really does work for any distance you choose. And so choose one that makes sense, where the numbers are easy to use. Honestly, I think this one, the numbers are easier to use. I just wanted to get through this quickly by showing it to you after the fact. All right, and that's it for that first complex constant velocity problem. Now, as I mentioned, despite the fact that I'd like everybody to get comfortable with the weighted average concept, I think it's important to realize you could always go back whenever you are asked for the average speed or average velocity, that you can always just go back to your good old-fashioned v equals d over t. You find the total distance, you find the total time, you divide them, no matter what. That will always give you average speed. Now, this is usually the time in the period when I give you an example of one of these to solve on your own. But we're not going to do that with this one particular problem, because in the packet, this one-dimensional motion packet, there are not that many examples of these. And I think the main thing about these problems in terms of like your ability to master them is really just putting you guys in a position where you're just practicing on your own at home. So again, the weighted average thing is important, but I think if you remember at the end of the day, v equals d over t is a thing that always works, that these will end up not being so bad for you. And with that, now we're moving on to the second and final complex constant velocity problem, which is the chase problem. And I call these problems chase problems to make them look exactly like they sound. A chase problem I refer to as a chase problem because the objects will be chasing each other. So essentially, there are two scenarios for a chase problem. The first scenario is the objects will start at the same location and they will end at the same location, but one of them will get a head start for a certain amount of time. So they will travel the same distance, but they will travel different amounts of time. The second scenario is where the two objects will be chasing each other, just like in the previous example, but one of them will get a head start in distance. So like imagine you were at school and you were standing at the corner of the school where the gas station is, and you were trying to run to the entrance of the school. This kind of chase problem, or this version of it, will be where one of you starts on the sidewalk in front of the gas station and one of you will start on the other side of Queens Boulevard underneath the train. So in one case, they'll travel the same distance, but somebody will get a head start in time. And in the other example, they'll travel for the same time, but one of them will get a head start in distance. We are going to go through both of these examples here conceptually and mathematically. But I want to write down a couple of things about these problems. So the first thing that we should say is that the two objects in a chase problem will be moving at constant velocities. So the relevant equation for these problems is going to be v equals d over t. The main work involved in this problem is visualizing it. It's figuring out what is happening at the beginning and being able to picture it. Because the next thing you have to do is you have to analyze the problem to determine what is the same about their motion, whether that's the distance or the time. That's what the slashes here mean, distance or time. And what's different about their motion, the distance or the time. So like I said, either they'll travel for the same distance, but they'll travel different times, or they'll travel for the same time, but they'll travel for different distances. Your job is to figure out which version of the problem it is. At the end of the day, I don't want anybody to get lost in the weeds conceptually. At the end of the day, the objects are moving at constant velocities. So it's a v equals d over t problem. But because you have two different objects, you're going to have a v equals d over t equation for each of them. Next point, for the quantity that is the same, you're going to set them equal to each other for both objects. So what do I mean by that? Well, let's just say, because v is equal to d over t, let's just say you happen to be doing a problem where they made it pretty clear to you that both of the objects were traveling the same distance, but one person got a head start in time. So if you know that their distances are the same, then what you really want to do is manipulate that equation, v equals d over t, and solve it for the distance. And you get d equals v times t. The main idea behind solving the problem then is to take the distance equation for each object and set them equal to each other. So you'd write something like d equals d. And I guess obviously, because that looks kind of silly, you'd write like d1 and d2. You don't always have to write 1 and 2, by the way. Sometimes they will say like it's cops and robbers, so you can put C and R as the subscripts. Or sometimes they'll say like Fred and Jane, so you can put F and J or something like that. And once you set the distance for those two people equal to each other, all you have to do is recognize that D is equal to V over T. So then the problem would transform itself to looking like this. You'd have D1 equals D2, and since D is equal to V times T, you'd have V1 T1 equals V2 T2. And depending on the specifics of the problem, you'll be given enough information where you'll be able to use that to get the answer. And the last point, as it says here, for the quantity that is different, you write an equation which relates the value of that quantity for one object to the other. What does that mean? Well, I'm going to stick with this example that I've used so far. In this problem, well, actually, let me back up for a second. In all problems, it has to be the case, if they are going to catch up to each other, which they always do in these problems, the chase always results in the person getting caught. In these problems, if the distance is the same, the times have to be different. And if the times are the same, then the distance has to be different. So let's say object 1, in this example where the distances are the same, object 1 gets a 10-second head start. And I'm going to write 10-second head S. 10-second head start. If object 1 got a 10-second head start, then that means object 1 and object 2 are going to be traveling for different amounts of time. This is when you're really going to have to think about it. Let's say that object 1 finished the race in 60 seconds. If object 1 finished the race in 60 seconds, I hope everybody realizes that when we say that that person got a 10-second head start, it means they were traveling for 10 extra seconds. So that means object 2 was only traveling for 50 seconds. And now you just need to write an equation to relate those two variables. Now, to be clear, I am giving these as an example. In reality, you're not actually going to know the times, but you can always write an equation for one time in terms of the other if you know what the head start is. So look at the 2 times we just made up here. If the one person got a 10-second head start, if they happened to be traveling for 60 seconds, that means the other person only traveled for 50 seconds. So that means that T2 is going to be related to T1 in a very concrete way, which is always determined by the head start. Now, if you think about it, up to what I've written so far, T2 equals T1, I hope everybody realizes that that is obviously not correct, because the person who we are calling object 1 traveled for 10 seconds longer than person 2. So we would have to take T1, which in this made up example we're saying is 60 seconds, and we'd have to subtract 10 seconds to get T2, which we're saying in this example was 50 seconds. So the fact that person 1 got a 10-second head start means whatever their time is, the other person's time is going to be that minus the 10-second head start. And once you have those 2 equations, you basically just solve it. I'll just give you a broad summary of how this would look before we actually go ahead and do one. You see how here, let's just say they told me velocity 1 and velocity 2. I'm in trouble because I have T1 in this equation, which I don't know. I made this up, so we don't actually know that. And we have T2 in this equation, which I don't actually know. I just made this up to illustrate the point. And if you only have one equation, but you have 2 unknown variables, you're stuck. But now that we have an equation for T2, in terms of T1, we can take that equation for T2 and substitute it in here. If we do that, now the only unknown variable in our equation will be T1. And we can go ahead and solve that for T1. And then once we know T1, we just come back here, take 10 seconds off, and that's T2. And then the whole thing is solved. That's the idea behind the chase problem. You have to think about what's the same about the objects. It's going to be either distance or time. You need to think about what's different about the objects. It's either going to be distance or time. And if some quantity is the same, like if the distance is the same, then that means the other quantity, the time, is always going to be different. And then you just set up the equations like this and you solve. I hope it's obvious to everybody, but I'm just going to point this out too, just so we're not confused. If they don't tell you which way the objects are running and you're trying to visualize it, it's very important to realize that if one person starts in front of the other, so like let's say this is person 1 on the left and this is person 2 on the right, if they're running to the right, that means person 1 has to be going faster. Remember, it's a chase problem. If the person who is behind is going slower, they're never actually going to catch up. So the faster person is always going to either be behind if the distances are different, or they're going to start later if the times are different. And honestly, that's about all I can explain about this without just showing you one and getting into the details. So let's take a look at an example of a chase problem. This example of a chase problem is kind of silly, strange story behind it. I was in the office one day with Miss Neron talking about physics textbooks, looking on her shelf at the different physics textbooks she had in there. And she pointed to a particular physics textbook and said, "Oh, this textbook is great. This guy explains things really good. I like this guy's textbook a lot." And I said, "Wow, it's really weird that you mentioned that because that guy was my professor in college." And this guy was weird. So the problems in his textbook are weird. So, fair warning. Chase problem example number 1. Thieves come roaring onto a highway at 100 kilometers per hour, headed for the Mexican border, which is 300 kilometers away from the highway entrance. The cops, in hot pursuit, arrive at the highway entrance 1/2 hour later. What must be their minimum average speed if they are to intercept the crooks on this side of the border? All right, let's take a look at this one.
All right, so in this problem, we have these thieves coming onto the highway, headed for the border, and it says that the border is 300 kilometers away from the highway entrance. I don't expect you to draw this out every time you have to do one of these problems, but I do think for this first one, it's probably a smart idea to just get a lay of the land over here. So let's say this is the border. I'll label that B, and this is the highway entrance. I'll just label that HE, highway entrance, and that's over here. And so the distance between them is 300 kilometers. And it says that once the thieves leave, and I'll just label that T for thieves, they travel a certain distance for a half hour, and then the cops leave a half hour later. So I hope everybody realizes that by the time the cops catch the thieves, they will have traveled the same distance. Because they start at the highway entrance, and let's say the thieves end up making it to here. The thieves making it to here is defined by the cops catching them, right? So the cops will have traveled exactly the same distance. I think it's good, even if you don't draw it, to sort of devise this mental image in your head, obviously a mental image, because it'll give you a sort of like mental or conceptual framework to be able to solve this problem. Additionally, I think once you start to get a feel for these problems, you will eventually realize that what's nice about these problems, or at least what's like makes them a little easier, is that whatever is the same about the motion of the two objects, either distance or time, whatever is the same, the other has to be not the same, and vice versa. And so I think it's pretty obvious from reading the question that the time is not the same, because it explicitly says the cops in hot pursuit arrive at the highway entrance 1/2 hour later. And so even if you weren't positive or didn't have this mental image worked out, even if you weren't positive that the distance was the same, the very fact that it is obvious that the times are not the same tells you that the distances have to be the same in order for this to work. The only other issue we really have to confront here, before we actually get into this problem, is why does the question say what must be their minimum average speed if they are to intercept the crooks on this side of the border? Why are they using the word minimum? If you think about it, I think it makes pretty good sense. The minimum speed that the cops must have would be the speed they'd have to travel at in order to catch the thieves just before they cross the border. Like right when they get to the border, they're just about to cross and then bang, the cops get there. So when they say minimum average speed, essentially what they're asking you to do is assume that the distance traveled is 300 kilometers. Obviously, if the police go any faster than the minimum average speed, then they will just catch the thieves further away from the border, or after having traveled less distance. Obviously, if they're going faster, it's going to take them less time to get to them, and so they will have traveled less distance. But when they say here things like minimum speed, and they give you a set starting point and a set ending point, they're asking you to assume that they've traveled the distance that they're giving in the problem. Okay, so what do we know about this problem here? Well, they tell us here that the velocity of the thieves, which I'll just put a subscript t. Of course, you could just put 1 and 2, but I think in the problems where they like explicitly tell you like what the person's occupation is, I guess, then you should just write that down and sort of help yourself to organize the information better that way. Obviously, you can just say thieves are 1, cops are 2, but I think it's easier to do it this way. So the velocity of the thieves, or the average speed of the thieves, as they say here, is 100 kilometers per hour. And as we established, the distance traveled by the thieves is going to be equal to the distance traveled by the cops, and since they call them cops in the problem, I'm just going to put a subscript C. That's 300 kilometers in this case. Obviously, as I mentioned, if they go faster, if the police go faster, then they're going to travel less than 300 kilometers, but because they're asking us for the minimum, that's our assumption. The last thing we really need to do to set this thing up is to think about the relationship between the times. As it says in the problem, the police arrive at the highway entrance 1/2 hour after the robbers. So in other words, the robbers get a half-hour head start. And so it's important to think about it this way, I think. Since the cops leave a half-hour after the thieves, whatever amount of time it takes the thieves to travel, the cops have to do it in an amount of time that is a half-hour less. So writing the relation for the times looks like this. The time for the cops is going to be whatever time it takes the thieves to travel minus 1/2 hour, and I'll just write 0.5 hours. And this question is asking us to solve under these parameters for the velocity or the speed of the cops, and so I will put that there. The key relationship here in this problem is that the distances are equal. And so that's where we'll start. We have the distance traveled by the cops is equal to the distance traveled by the thieves. Since V is equal to D over T, I'll just show this here, so I don't want to confuse anybody, although I'm sure this is clear to you. Since V is equal to D over T, that means D is equal to V times T. You don't need to show that, though, because as you'll see, this problem's a decent amount of work. And so I'm just going to assume by now that you know that. So we have the velocity of the cops times the cops' time is equal to the velocity of the thieves times the thieves' time. And this is why it's really important, I think, also to use an uppercase T for the subscript for thieves, because that would just look a little confusing if they were both lowercase, perhaps. And so now we can make some substitutions, right? Because I know that, I don't know that, I don't know that, and I don't know that. So I have to work with this equation a little bit and set it up and make it a little easier to use. And so what I'm going to do here is I'm going to substitute in my expression for TC. TC, as we said, is the time for the thieves minus a half hour. So I'm going to put the time for the thieves minus 0.5 hours. And that's equal to the velocity of the thieves times the time for the thieves. Notice, by making that one substitution, I've reduced the number of unknowns in this equation by 1. Now, there are a lot of ways that you can approach this, but this problem is actually a little bit easier than it may look. and is probably one of the easier chase problem examples that you'll see. And the reason why it's a little bit easier is because they told us this, actually, because we can use that. As a general rule, you then want to take this velocity or the speed and factor it to both of the, not factor it, excuse me, distribute it to both of these terms here, but you actually don't have to do that. Since the problem is asking me to solve for the speed of the cops, I'm just going to go ahead and solve for the speed of the cops. VC, the speed of the cops, is equal to the velocity of the thieves times the time for the thieves over this whole thing, right? Because these two are multiplied, I'm just dividing everything in the parentheses to the other side. So I have the time for the thieves minus 0.5 hours. That's an equation. It will tell us every single thing we need to know. But there's a problem. We know that, the velocity of the speed of the thieves, but we don't know the time it takes them yet. So what I'll write here is we need to find the time for the thieves. And the reason why I said a minute ago that this problem is actually easier than most other chase problem examples is because we actually have enough information to do that. And the reason why we have enough information to do that is because they gave us the distance traveled by the thieves. So I'll just write here, you don't need to show multiple unknowns. That's the thing they're asking us to solve for, but just so we can keep track of it, the time for the thieves is going to be able to be solved for using the velocity of the thieves and the distance the thieves travel. So since v equals d over t, we know that t, by solving this equation for t, bringing the t up and over and the v down below, t is equal to d over v. So I'll rewrite this over here as the time for the thieves is equal to the distance for the thieves over the speed of the thieves. And plugging that in, we have the distance for the thieves, which is 300 kilometers, over the speed of the thieves, which is 100 kilometers per hour. This math is not particularly difficult here. 300 divided by 100 is 3 hours. And now that we know the time for the thieves, we can jump back over to this equation and wrap this thing up. So I'll rewrite the equation here. We have the speed of the police is equal to VT, speed of the thieves, times the time for the thieves, which we now know, over the time for the thieves minus a half hour. And so we have the speed of the cops is the speed of the thieves, 100 kilometers per hour, times the time for the thieves, 3 hours, over 3 hours minus a half hour, or 2.5 hours. And when you take 3 divided by 2.5, and you multiply it by 100, you get the speed of the cops, which is 120 kilometers per hour. And that's it. Now, as it turns out, in general, I regard this problem as being a little bit easier because they told us the distance they had to travel. But in general, this basic setup is the way you do all these problems. What's different about this problem than most other problems is that most other problems, instead of giving you the distance, they give you the other velocity and ask you to solve for a distance or a time. And so as we go through the variations of these problems, I hope you realize the main points. Figuring out what's the same, figuring out what's different and how they relate to each other, and recognizing that V equals D over T is the name of the game. A word of caution: do not get discouraged if you find these as you do them on the homework to be kind of difficult, because these are kind of difficult. Of all of the things that we do this year, this one actually usually gives kids more trouble than any other kind of problem. I don't really get it. I personally, I think there are other problems that are harder than this, but I just want to make sure that everybody is just keeping in mind that this is going to take a little time for some of the harder versions of this problem for you to get used to. But if you persist and you practice and you try to apply the framework that we have come up with here, then I think you'll be fine. The main point here, though, is that the visualization of the problem in the beginning, even if you have to draw it, that's key to being successful at how to solve these. Before I have you solve one of these on your own, I want to show you one more problem that's a slightly different variation. So let's go take a look at another problem.
This problem says a police officer is sitting on the side of the road with a radar gun pointed at the oncoming traffic. In a 40 meter per second speed zone, a motorist zooms past the police officer at a speed of 57 meters per second. As soon as the officer measures the motorist's speed, the officer begins to accelerate in order to pull the motorist over. Once the police officer has reached a sufficient chase speed, 73 meters per second, the speeding motorist is 450 meters ahead of the officer. And the question says, how far must the officer travel before he or she catches up to the motorist? Let's take a look at this one.
Okay, so in this problem here, we have a police officer sitting on the side of the road. Car drives past. Of course, because we have to be a little realistic about this problem, though, we have to account for the time it takes for the police officer to accelerate before they can start catching up to the speeding motorist. And so as the problem says, the police officer accelerates, and then they reach a constant speed of 73 meters per second. And by the time the police officer has reached that speed, the speeding motorist, it says motorist here, so I'm going to just put the subscript M, only because the unit for time is seconds, and I don't want to have too many S's floating around. By the time the speeding motorist is about to be pursued by this police officer, they're 450 meters ahead of the officer. And so the question here is asking about the distance that must be traveled by the police officer from here before they can catch up to the motorist. So let's take a look. Again, I think it's always good to consider that visualization piece before you do these. So what do we know? Well, we know that the velocity or the speed, I keep saying velocity, but I should be saying speed because they're not giving us directions. We know that the speed of the motorist is 57 meters per second. We know once the police officer reaches the chase speed, and I'm just going to write V with a subscript P here. We know that once the police officer reaches the sufficient chase speed, they've reached a speed of 73 meters per second. And we know that the distance is different. And if we know that if the distance is different, the times have to be the same. If you don't realize why the times are the same, well, let's go back to the visualization for a second. Here's our 450 meters. As soon as the police officer reaches the chase speed, you can think about the stopwatch for this problem starting. The motorist is going to travel for a certain amount of time. The police officer is going to travel for a certain amount of time. Notice here, the distances are different, but the amount of time between when the stopwatch starts, when they're both here, and the amount of time once they reach the same spot, that's the same for both of them. So the times are the same. The distances are different. And you know what? I guess I'll just leave that here for a second while we write this next part, because the next thing we have to do is consider the relationship between the distances. I think drawing those arrows is pretty helpful also. Notice here, it doesn't really actually matter which way you do it if you write an equation for the distance traveled by the motorist or the distance traveled by the police officer, but just because, whatever, I've decided, I'm going to write the distance of the motorist is equal to. I think drawing these arrows is super helpful because the police officer's distance, shown by this middle arrow here, can be broken up into two segments. The part that is exactly the same as the distance the motorist travels, and that 450 meters. So the distance the motorist travels is equal to the distance the police officer travels minus that 450 meters. If you stop there and take a second to realize that, to think about that, you realize that that makes sense. Because notice what that's saying is that the distance the motorist is traveling is the distance the police officer is traveling minus something, which tells you that the motorist travels less distance than the police officer. And you should always realize that that makes sense because the person who's behind has to travel more distance in a scenario like this. Notice we could confirm that if we just add the 450 to the other side. It says the cop travels the distance the motorist travels plus 450, which makes sense because the motorist got a 450 meter head start. And what this question is asking us for, how far must the officer travel before he or she catches up to the motorist? What they're asking us for is D with the subscript P, the distance traveled by the police officer. Okay, so the first thing we can do here is we can acknowledge the fact that the times are the same. I'll do this over here just in case this needs a lot of room. We'll have the time for the police officer equal to the time for the motorist. I'm going to show this again just to make sure everybody's with me, but you do not need to do this every time. Because V is equal to D over T, doing a little bit of algebra reveals that the time is equal to the distance over the speed. So T is equal to D over V. So I can rewrite this over here as dP over Vp equals dm over Vm. But of course, there are variables here that I don't know, specifically 2 of them. And so I'd like to make my substitution. Notice I know the speed of the police officer, I know the speed of the motorist, but I don't know either of these two distances. But I know how they're related. And now I have an equation for one in terms of the other. And that's a nice little thing. So there are a lot of ways that you can do this. You can make the substitution for the distance traveled by the motorist immediately. I don't recommend you do that. I recommend you cross multiply first, just because there's less writing. So I have to cross multiply. This part of it's going to look funny because you're now going to have different subscripts paired together, but that's a way that you can always remember to tell that what you're doing is correct. It just something seems weird about P's and M's being on different sides of the equation when they're all together like this, but either way, that's the correct cross multiplication. We have the distance traveled by the police officer, speed of the motorist, and then distance of the motorist, speed of the police officer. Okay. So to wrap this one up, we just need to sub in the distance traveled by the motorist. So we have the distance traveled by the police officer times the speed traveled by the motorist is equal to the distance traveled by the motorist, which we said is the distance traveled by the police officer minus 450 meters, and then multiplied by the speed of the police officer. What makes this version of a chase problem a little more annoying is that now we have to distribute. And that just gets a little funky. Just be careful. You know how to do this. We have the distance traveled by the police officer times the speed traveled by the motorist. Then when we distribute, we have the speed of the police officer times the distance traveled by the police officer. And then we'll subtract the speed of the police officer times 450 meters. But now, notice, and this was the whole point of this problem, but we have a little bit of an added difficulty because now the variable we're trying to solve for, the distance traveled by the police officer, appears in two parts of our equation. So I have to gather those terms before I can solve for it. Now, I'm going to give you a piece of advice that you may find stupid, but I'm going to give it to you anyway because I would like to avoid you all making a silly mistake. There are obviously two ways that I can do this. I can subtract this term, VP dP, to the left-hand side, which is less work, or I can subtract this term to the right-hand side and then add this term and bring it to the left. Obviously, that's like a little more work, but that is the recommended method. Because a lot of people, when they just subtract VP-DP over to the left-hand side, drop this negative somewhere. And then they end up getting a negative distance. And because like distance is a scalar, that really makes no sense. So please, I recommend that you follow that piece of advice. I'm going to add VP times 450 to the other side. And since I'm going to subtract the dpVM term over to the right-hand side, I'm just going to leave this on the left-hand side alone. On the right-hand side, I'm going to have VP dP, and then I'm subtracting that over, so that would be minus dpVM. Let me make that uppercase so it doesn't look like a meter. Okay. Now, I'm just going to switch the order of these because I like to have the thing I'm solving for on the left-hand side. And I'm going to factor it out. But I'll just rewrite this up there first so I don't lose anybody. So I have VP dP minus dpVM, which is the part of this that looks weird because they're together and then they're separate. Don't let that confuse you. And then we have VP times 450 meters. And in order to solve this for the distance traveled by the police officer, I just have to factor it out. Both terms have a dP, factor it out. That gives me VP minus VM. This is what I was talking about before, by the way. Notice VP is bigger than VM, so that difference will be positive. If you did it the other way, this would have been negative. That would have canceled that negative sign over there. It's not impossible. Like, it's a little annoying. And then that's equal to VP times 450 meters. And to wrap this one up, I just got to divide by the difference in those speeds. So I have VP times 450, 450 meters, by the way, and then over VP minus VM. Again, I'd like to make that look less like a meter. And plugging in, I have VP 73 meters per second times 450 meters over VP 73 meters per second minus the speed of the motorist, which is 57 meters per second. And when you do that math, 73 times 450 over 73 minus 57, you get 2,053 meters, which, since the two speeds given and the distance given, since these two have two significant figures, we'll just call it 2,100 meters. And that's it. I warned you. The first example we did was a little less complicated than this. But it's important to realize, if you're careful with your distributions and your factoring, once you get the practice with this, it's not actually so bad. Another thing I'd like to mention very quickly before we wrap up this particular problem is that there's a secret shortcut. And the secret shortcut is real, real nice.
All right, everybody, that's it for today. This video is getting a little long, so I guess we'll just leave it there. And tomorrow, once the video begins, we'll get the chance to have you solve one of those on your own, and then that'll be it for the chase problem. Have a good one, everybody.